Now that we know something about polar functions and polar coordinates, let's apply some of the calculus techniques to it. Here we see the key idea for finding the slope of a curve that is defined with polar coordinates. And for an example, let's find the equation of the tangent lines to this graph r equals to cosine 2 theta. As you can see, I have a picture of r equals cosine 2 theta and a tangent line there. But at any particular theta, how do we know what the tangent line is? Well, let's first find the slope. So in our particular problem here, we have our graph r equal to 2 cosine theta. Now above, we need to unravel what this means, right? What is x and what is y? Well, for us, x is equal to, what is f of theta? F of theta is cosine 2 theta. Right? And that's times cosine theta, r cosine theta. And then y is r cosine 2 theta times sine theta. And so in our particular example here, the function that we're calling f of theta is cosine 2 theta. So we need to have its derivative. We need to find its derivative. So that would be f prime is equal to negative 2 sine 2 theta. So now we're actually ready to apply this formula. Okay, so we have the derivative, negative 2 sine 2 theta times the sine of theta plus cosine 2 theta times cosine theta, all divided by negative 2 sine theta, 2 theta, that's the derivative, times cosine, and then the function itself, cosine 2 theta times sine theta. So that's it. And the important part here is really understanding where this comes from, right? And the book has a really good explanation for that in a video. This is just how you would apply it to a particular function. Now that's a bit messy, and most of the time when you're dealing with polar curves, you are going to have a bunch of sines and cosine thetas around. And you should recognize this as a good place to apply maybe a trigonometric identity to simplify it a bit. So I did that below here. I applied the product to sum formulas, and I just, you can see that it simplifies down to this. And that is the slope at any particular theta. So that's great. So what about the tangent line? Well, the tangent line, we have the slope and we need a point. So for some theta between 0 and 2 pi, what's the tangent line? The tangent line would be y minus the y value. But what was the y value? We found that. That was r sine theta. So that was cosine 2 theta times sine theta times the slope, which we have above here, cosine theta minus 3 cosine 3 theta all over sine theta plus 3 sine 3 theta times x minus the x value, which is r cosine theta. So that's cosine 2 theta cosine theta. Now, if you want to know the slope of the tangent line when theta is pi over 4, you just put pi over 4 for theta. Okay, and so what I did is I actually created a graph in Desmos of this exact function. Right over here. And what you see is the r equal cosine 2 theta. And if we were to turn on a point, so this is just a point on the graph. A is theta, so that's why I just let A be the angle in here. And we can see that we'll have an x comma y. X is r cosine theta, r sine theta. And you can see it's spinning around the flower like this. Now what about the tangent line? Well, this is the tangent line that we just found. And if we turn that on and we let our theta vary, we can see the proof is in the pudding. We can see that the tangent line that we found using calculus and algebra indeed works, right? It indeed is the tangent line to this graph at any particular theta. Okay, now let's look at the area of between polar curves. Here we have a nice formula for the area. This comes from looking at the Riemann sum of polar rectangles. I encourage you to look at that. But for an example, let's find the area of all the petals in the flower that we just found, r equals cosine 2 theta. So how do we go about doing this? Well, in this case, if we were to take a typical theta, and I encourage, this is what I always do just to make sure I have the integral set up right, is just take some theta. That's a ray, right? Theta equals some theta. And then look at the outside r and the inside r. Okay. So here, in this case, we have an outside r, right, which we will call r2. So that distance there is r2. But there is no inside theta. R1 is equal to 0. So in this case, R2 is the outside function, which is defined as cosine 2 theta. And then the inside function is just 0. So when you have some polar petals, you maybe have a bit that's on the outside, but then it stops. So you would have a positive R1, which would also be a function of theta, but not in this case. So in this case, we just write the integral. So I'm going to do a trick and use symmetry. You can see that if we found the area of just a half of one of these petals, just like this, that if we doubled it, we get one petal, and times 4, we get all of them. So that 8 of those will be the area of everything. So I'm going to use that. Okay. So the whole area of the entire thing is 8 times the area of one of those petals. But the area of one of those petals is, apply the formula above, is 1/2 times the integral. Now I'm just going to integrate theta from 0 to here. Okay. And that's theta equals to pi over 4. So I'm going to integrate from 0 to pi over 4 of r2 squared. Right? So that's cosine squared 2 theta d theta. And that's it. And that's a fairly simple integral. We just get 4 times the integral from 0 to pi over 4. And here we get 1 plus, I think we get the cosine of 4 theta all over 2 d theta. Right? And that's 4 times 1/2. Well, let's bring the 1/2 out. Right? We have this whole thing's 1/2. We bring the 1/2 out, and that's 2. And then we have the integral of 0 to pi over 4 of 1 plus cosine 4 theta d theta. And that ends up being 2 times theta plus sine 4 theta over 4 from 0 to pi over 4. And in this case, sine of 4 theta is sine of pi when pi over 4 is in there, and 0. So this just ends up being 0 for pi over 4 and theta. So you end up getting, when you put this in, pi over 4, you get pi over 4 minus 0, so you just get pi over 4. So 2 times pi over 4, which is equal to pi over 2. So that is the total area of all of the petals in this example.